Okay, welcome everyone. Good evening. Welcome to this month's quantitative finance seminar here at the Fields Institute. Before introducing our speaker for today, I would like to thank our sponsors, Waterfront International, as well as Scotiabank through the Center for Financial Industries for their continual support of this seminar series. So today we have a really great treat. We have Professor Zhou from Columbia University, and Professor Zhou is the Liu Family Professor of Financial Engineering and the Director of the Knee Center for Intelligent Asset Management at Columbia University. His research develops foundational theory for continuous time reinforcement learning and its applications to financial decision-making, building on his influential work in stochastic control, time inconsistency, and quantitative behavioral finance. As a fellow, he's a fellow of IEEE and the SIAM. He's received numerous honors, including Royal Society Wolfson Research Award, the SIAM Outstanding Paper Prize, and Columbia's Distinguished Faculty Teaching Award. That one's pretty interesting. I think that's going to play a big role here today.
Okay.
And today, Xunyu is going to tell us about data-driven Merton strategy via policy randomization. So please join me in welcoming Xunyu.
Okay, thank you very much, Sebastian, for the very nice introduction, and also for inviting me to give talk at the Fields Institute. Of course, I have spoken several times in this, in this place, and I always like to come back to Toronto. And actually, I was telling Silvana and Sebastian, my second job after PhD actually was in UFT, University of Toronto. Now at that time there was no Rotman. At that time it's called the Faculty of Management. There's no Rotman actually. I think Rotman is something later, right? So that was 1991 to 1993. So that's a very beautiful memory. Toronto. I really like the city. Okay, great. So today I'm going to talk about this Merton strategy. This is a joint work with several people. So Min Dai is from Hong Kong Polytechnic University. Yu Chao Dong is from Tongji University in Shanghai, and Yan Weijia is also from Hong Kong, Chinese University of Hong Kong. Okay, so let's start. Okay, so this is the plan. So I will start with the story, right? Background, motivation, and then I will formulate the problem. And then I will present the theoretical analysis, followed by algorithms, the reinforcement learning algorithms. And if I have time, I'm going to talk about, present some simulation and empirical study results. And then I'll conclude, okay? So it's a long agenda, so you see how far I can go. All right, so background and motivation. Okay, so I think we are all very familiar with this traditional so-called plugin paradigm, okay? So by that, I mean, you have a basic stock price model, right? Let's say it's diffusion model, jump diffusion, Markov chain, whatever, right? And then an econometrician estimates model parameters or primitives, right? So estimate those parameters of the model. And then a theorist, me being one, okay, plugs in estimated values and solve a stochastic control problem. Okay, so this is how we solve the problem all the time, right? But however, for financial markets, among many other problems, not only financial problems, accurate estimates of certain parameters require amount of data far beyond history of financial markets, which I will explain actually using a simple example. And then the other one is, of course, non-stationarity. Okay. So therefore, the thing is, it's very difficult to estimate the certain parameters. But on the other hand, optimal strategies, for example, Merton problem, Markovich problem, the optimal strategies and values are very sensitive to model primitives. So meaning that if your estimation is wrong, then your solution is wrong, because it's very sensitive, right? So you have a wrong model, your solution is totally wrong, can be way off, okay? So that is kind of a very big problem, okay? So let me use a simple example to illustrate this, okay? So suppose let's talk about a stock, right, whose yearly rate is RY, okay? And then this is estimated through 12 monthly return, RI. So each RI is a monthly return, and the RY is a yearly return, right? So if those RIs are small, then of course we can ignore those cross terms. So the yearly return is roughly the sum of the monthly return, right? So think about like 1% monthly return. So yearly return is 12% roughly, right? Okay, so we have that. Now assume all those monthly return are IID, so with mean R bar when R bar 12 means you have 12 months, right? Sigma square, so that's variance, and they're mutual, they're IID, for example. And then of course you take a mean, you take a variance on that equation, that equation, and then you get this, right? So that's very simple calculation. So therefore, that means the mean monthly return is 1/12 of the mean annual return, and the standard deviation, the monthly standard deviation, is 1 square root of 12. That's square root of yearly standard deviation. Yes. Okay. So you can see that there is an inconsistency between these two factors, and that causes problems. Okay. So I will show you. You can extend this to a general case. For example, if the period is 1/n part of year, right? Then similarly, you have this, by the same token, right? You have this. So therefore, so if we divide Rn by sigma n, so that is what? That is so-called signal to noise ratio, right? Because Rn bar is the, let's say, monthly return, right? Sigma n is the standard deviation of that return. So this is so-called signal to noise ratio. And that signal to noise ratio for the small period, the period is 1/n part of a year. So that is square root of 1/n of the yearly signal to ratio. Yes? I can see this. Because so therefore, when n goes to infinity, this signal to noise ratio decreases dramatically. When n goes to infinity, it goes to 0 as the period length goes to 0. Now, what does that mean? Let's first look at some numbers. Okay, so for a typical stock, let's say annual return, mean return is 12%. Like Apple stock, right? 12%. That's pretty stable over the years, 12% roughly. Standard deviation 15%. So this signal to noise ratio 0.8. So that's very standard. That's very normal. But let's go down to monthly. Okay. So the monthly becomes 1% and 4.33%. So this ratio becomes 0.2309. It's much less. It becomes smaller, right? And then let's look at daily. So we think about daily return and daily standard deviation. Okay, so 250. So assuming that there are 250 trading days in a year, then this ratio becomes 0.0505. Now, what does that mean? That means you don't know where this R bar is, the mean where it is. So it is like it is like a needle in an ocean. You don't know where it is because this ratio is so small. And if you think about even like every minute or every second, and that ratio will be even smaller. Okay, so therefore the conclusion is it is meaningless to even talk about the mean return for a small period. It is just noise because the signal to noise ratio is too small, so it's just noise. But that aligns with our sort of. I mean, if you trade stocks, you will see Apple. Now, Apple is supposed to be a very stable stock, right? But can easily, a daily move can be 4%. Can be easily 4%. Today go up 4%, tomorrow go down to 5%. Can be easily, right? But the mean probably is only 0.048% daily. Okay, so in other words, when you talk about the daily return, all you see is noise. Okay, and you don't know where the mean is because the signal to noise ratio is so small. So, like I said, it's like a needle in the ocean. You don't know where it is. Okay. Now, you can look at this problem from a different angle. if you want to get a good estimation of 1% monthly return stock with an error of 0.1%, so this is not a very good, very accurate estimation, right? It's just 1/10 of the value. The error is 1/10 of the value. If we want to achieve that kind of accuracy, which is not very demanding really, it requires 150 years of monthly data. That's in Lundberg's book. But we don't have a stock market with history of 156 years, right? So meaning that if we only want to estimate, a monthly return, it is almost impossible. We don't have that kind of data. Okay, all right. So therefore, if you further go down to the so-called continuous time, think about high frequency trading and so on. So this time period is even smaller, right? It's like a millisecond, right? So we have continuous time model. The drift code, so this is called the drift, right? In the SDE. So drift is what? So this is the mean rate of return per delta t. That's delta t is very small. So the drift coefficient mu in a stochastic differential equation is a pure noise. It's just noise. Okay, for the same reason. Or it requires an infinite amount of data to pin it down. In other words, only God knows. Nobody else knows what this mu is. So when you say, I estimate this mu, it is meaningless. It is impossible. This number mu, okay, the drift. All right? But like I already said, many model-based financial decision-making problems are highly sensitive to model parameters, meaning that their solution depends on the value of mu. But if the mu is meaningless, what do you mean by your solutions, right? So you see, this is a problem. All right, now I can also show you another example, which is a kind of simulation. Right? I simulate 8 years of monthly return rate using exactly a normal distribution with mean 1%, standard deviation 4.3%, which is very normal, as I already said. And then we use sample mean and sample standard deviation for each year. Okay, so let's look at this. So all these numbers are sampled from this normal distribution with mean 1% and standard deviation 4.6%. So we have this, all these samples, right? So if we add, let's say first year, you add all these up divided by 12 data. So this is a sample mean 3.02. So this is way off, right? Because the true mean is 1%. Okay, so way off. And then it's all over the places. You see, second it becomes 0.52. All right. Now, even if let's say you add all these up and divide by 8 years, you got 1.32. And that is still not good, right? Because remember the true mean is 1%. So this estimation using these number of data, it's 30% off. 30% off, right? On the other hand, the standard deviation is pretty okay, 4.12. The true value is 4.33, right? So that is okay, pretty good. And people know that you can estimate the variance, the standard deviation quite accurately using sample variance, but not the mean. Okay, so from here you can also see this. So this is where this so-called reinforcement learning or RL paradigm comes in, all right? So RL takes a conceptually and a fundamentally different approach from the model-based plug-in approach, the traditional approach. Now, again, it has a basic structure model, again, diffusion, jump diffusion, whatever, right? It does not assume model parameters to be given and known. So no longer we assume that those are known, nor does it attempt to estimate. So I don't even estimate because it's, as I explained, it's impossible to estimate them for some parameters. So let's just skip it. Let's just give up estimating those parameters. RL learns optimal policies or strategies directly. So I just learn my optimal strategies directly. So forget about model. Okay, forget about estimating models. Specifically, I can parameterize a policy. A policy basically is a function, so I parameterize it and then update, or as we say, learns it. Like it learns its parameters iteratively to improve until optimality or near optimality is achieved. Okay, so it goes down a completely different route. All right, now there's another aspect in, important aspect in this RL approach. And let me explain this using this so-called bandit problem, okay? So this is multi-arm band. So this bandit has many arms, okay? The question is, so these are the slot machines, right? And each machine has different winning odds, which can be adjusted actually, right? So the bandit doesn't know about the winning probabilities of each. So he certainly it does not know. Now the question is how you should play. You should play those machines in what order in order to maximize your game. Okay, that is the question, right? Now, if you were, the bandit, or if you're a gambler, right, going to Las Vegas, you see those machines. What would you do? Well, I would probably try each machine a little bit, right? See which one gives this so-called lucky machine, right? To see which machine is good. So suppose you have enough money to play around. So you play each machine, let's say 100 times, right? Each machine 100 times. And you found that the first machine has the best payoff out of these 100 times. And then if you are following this model-based approach, then you will think, okay, the first machine is the best, right? That's like an estimation. We use the past data to estimate the winning probability of those machines. And if the first machine is the best out of this 100 trial, and then I stick to the first machine, right? Is that what you do? Now, of course, at least I do not have that kind of money to waste, each machine to play 100 times, but maybe each machine plays like 5 times. And then I just stick to one machine, right? That's what we typically do. And that is a model-based approach. Now, the danger of that is the first machine may not be the best machine, right? Even if you played 100 times, 1,000 times, 1,000,000 times, it's the best. It does not necessarily mean it is best, right? Okay. So the reinforcement learning approach to this problem is to apply the so-called Ipson-Guidi strategy. Okay, Ipson-Guidi strategy. That is to play the current best machine. Let's say current best machine is the first machine. So yes, indeed, I play the current best machine, but with some probability. So I design coin. Okay, I design coin. So Ipson is a small number. Let's say 0.05. So I design coin. The head, has a probability of 95%. The tail has a probability of 5%. Okay, so then every time I flip a coin. So if it is head, then I play the first machine. But if it is tail, then I play the other 7 machines uniformly. It's random. So this is called Ipson-Guidi strategy. Okay. Now this way, you still kind of focus on the first machine because that's the most promising machine so far. But you still give chance to the other machines, right? Because it's possible that the best machine is in the other machines, right? Okay. So therefore, you can see here the difference between this approach and the model-based, the plugging approach. Plugging approach, basically, you first explore, and then you exploit, right? Exploit means you optimize. You first determine which one is the best, and then you just exploit that information. But this Ipson-Guidi strategy is you explore and exploit all the times, and at the same time. You always explore, rather than you first explore and then exploit. Okay, so this is the difference. Yes, this is the difference between the two. And you think about this Ipson-Guidi strategy is a randomized process because you flip a coin. You toss a coin to decide what to do, right? And that captures the idea of trial and error because you want to see the kind of counterfactual, okay? Because if you stick in the first machine, then you don't see the other machines. You don't see the counterfactual. So by flip a coin, you have chance to see the counterfactuals. And that is the idea of exploration, okay? So this is randomized policy or strategy that captures trial and error, to experience counterfactuals, okay? Now, I think this is very important. This is very important point, bullet point. You see, in this approach, the gambler just learns the best randomized policy instead of learning model. So the gambler now focus on how to design this coin. For example, what should be this epsilon? Whether this epsilon should be 0.05 or 0.01. Or maybe better yet, as you play along, whether this epsilon should be decreasing, right? You start with epsilon pretty high, 20, let's say epsilon is 0.2, but as you explore more and more, you decrease that. So how do you design that epsilon or that sequence of epsilon? That is your problem. I'm no longer interested in knowing the winning probability or estimating the winning probability of those machines. You see, I skipped that part. I focus on my strategy. In this case, it is this epsilon. How am I going to decide this epsilon, right? That becomes my problem, okay? So this is the main idea of RL. Basically, this bandit problem is a precursor of reinforcement learning. Okay, so now I can summarize a bit, the key steps in reinforcement learning. Exploration, you first do exploration, try and error, right? So you randomly experimenting different actions according to some probability distribution, okay? So in that epsilon gradient, that's like this coin, right? You design that coin. So it's called randomized or stochastic policy, and then observing the response. The response is the response from the environment, which is unknown. It's called the reward signal or reinforcement signals. And then you try to improve yourself. Okay, so the first step is exploration. The second one is policy evaluation. It's called PE. So you learn the value function of that stochastic policy based on reward signal. So based on those reward signal, you decide the value function of this coin. So let's say you have a coin, right, with 95%, 5%. So what is the value function of that coin? Okay. Now here, by the way, the value function is not the optimal value function, as we know. I mean, in the stochastic control, mathematical finance community, value function typically optimal value function, right? But in computer science community, value function is objective function. Okay, so we make use of their terminology, their jargon, so as to be friendly to them. Okay, so this is policy evaluation. And the next is policy improvement. So improve the stochastic policy, improve. So you want to make a better coin, right? You improve the stochastic policy based on the learned value function. So once you have learned the value function, then you try to improve it. So it's called policy improvement. And the final kind of component is the convergence and regret analysis. Because this reinforcement learning is inherently iterative. It's iterative. So therefore, you want to make sure that this iteration will converge, right? So there's convergence and also so-called regret analysis. That is the convergence of the policy parameters and the loss of objective value compared with oracle access. Now, oracle access means if you are God, you know this mu, right? So there's what do we call the oracle solution? But of course, we don't know oracle solution. We can only use this iterative scheme, RL iterative scheme, to achieve a value, right? So what's the difference between the two? Okay, so this is called the regret. So what is that regret? So basically you need to know how good your approach, right, your algorithm is, basically. Okay, so these are the key steps in RL. So I can summarize now. The model-based stochastic control include like a Bellman principle. I assume most of you are familiar with that. Bellman's principle, dynamic program principle, HJB equation, PDE, verification theorem, or maximum principle, BSDs, FBSDs. Those are like traditional model-based approaches. But the issues are there are model misspecification, the misestimation, as I already explained, right? But there's another big issue, which is even if, let's say, you know every parameter accurately, and then you have to solve the HJB equation. HJB equation is PDE. And PDE has this problem of a curse of dimensionality. So if the dimension is more than 4, you have a problem computationally, right? So there's a curse of dimensionality problem. So there are two problems, actually. And the RL goes down a different route. exploration, policy evaluation, policy improvement, regret analysis. And that actually solved the previous two issues at the same time, because it also get around the curse of dimensionality. All right. So this is the comparison between model-based and model-free approach. So in the past few years, I think we started our research in like around COVID, pre-COVID, 1999 or something. Our first paper published in 2020. So these 5 papers, each paper addressed one issue. Okay, like the first paper addressed the problem of how to do exploration strategically. You don't want to do exploration blindly. You want to do it strategically. And so what is the best coin? Or what is, in general, what is the best distribution, exploration distribution, right? And then the next is policy evaluation, policy gradient, Q-learning, and the final paper is the regret. Okay, so I call it a pentalage. So this is our reinforcement learning for control diffusion process, continuous time, diffusion processes. Okay, now there is one question to ask. Okay, so coming back to the investment problems, right? So you may say, yes, if we are a big shot, right, your action, your investment strategy will affect the stock price. So therefore, your action will affect the pricing environment. And then it is necessary to do exploration, right? Because you want to see the counterfactual. If we don't explore, you won't see those counterfactual, right? But whether those randomized policy necessary for small investors, whatever I do, my action will not affect the stock price. I'm a small guy, right? So whether I still should do the randomized policy, right? That's a question. So primary goal of randomized stochastic policies is for exploration, right? That is to experience counterfactuals. So it is relevant for example, Merton problem with a large investor. But it seems that it is unnecessary for a small investor because there's no information, no benefits to take stochastic policy or reinforcement learning. Yeah, as I said, because your action will not affect the environment. Yes? Well, actually, one of the key points of this paper is we show how randomization can still be used to solve Merton's problem efficiently and effectively in a model-free, data-driven way, even for small investors. Okay, so I want to make a point of this. All right. Sorry. Yes, sure.
Silly question.
Sure. No question is silly.
Whether your action affects the system, the relevant question to ask whether to use RL or not. Here's where I'm coming from.
Yeah.
In the bandit problem.
Yeah.
The action doesn't affect the system, but yet it's still useful.
Correct. But if you don't try other, you don't try other arms, you won't see the results, right? Because remember, you say, oh, the first machine is the best, so I stick to that. So you won't see the counterfactuals, right? So in this case, the context is like this, because you wouldn't see if you don't play the others, you wouldn't see the counterfactual. The keyword is counterfactual. Okay, agree? Now, in the case of stock market, if you are a big investor, if you don't randomize your policy, you won't see the counterfactuals. But if you're a small investor, no matter what you do, you don't see those counterfactuals anyway, because whatever action you take, your action has no price impact, right? So you wouldn't see the counterfactual. You see, I want to see if I do this, then what is the price reaction if you are a big investor? So in that sense, yeah, in that sense. Oh yeah, but
I could view different stocks as different arms of the bandit, and I would still learn something by randomizing over.
No, in this case, the different stocks are not different arms.
No.
Rather than it's a different actions, right? Different portfolios.
Okay.
Yeah, different portfolios. So in the context of stock, in the context of stock trading, the price impact is the one that affects the counterfactual. I think. Yeah, I think that's what I try to say. Yeah. But that's very good question. Yeah. All right. Okay. So now I have a long story. I really had a long story to tell. So now let's see the formulation, okay? So Merton problem, okay? So first, let's see the market. So just assume there are two assets, right? One is risk-free, the bond with rate R, and the stock, just index, for example, just index, right? So stock price, of course, is observable. So follow this, SD, yeah? And there's a factor, X. And X, again, is also observable. We assume X is observable here. And X follows another SD, okay? And here, B and B2 are two independent Brownian motions, okay? Right, rho is the correlation coefficient, right, between -1 and 1. So therefore, you can see the market is in general incomplete, right? Incomplete. Now here, assumption is we can estimate the volatility process, sigma. Sigma can be estimated. As I said in the very beginning, sigma can be reasonably estimated. So we assume sigma can be estimated or observable even. Yes, estimate through quadratic variation or observable. Let's say you can use like a process like VIX. Okay, so just you use that as a proxy, right? But however, all the others, mu, m, nu, or even rho are unknown. These are unknown because the drift, we already said these parameters are difficult to estimate. So those are unknown.
But if I can estimate sigma from quadratic variation, why can't I estimate nu?
Oh, yeah, I already explained in the very beginning. The mu can be estimated.
No, nu.
Oh, nu you can, yeah. Nu is not a big deal, yeah. You can see nu is not, yeah. Yeah, but in our setting, nu can also be unknown. I know, yeah. Nu can be unknown. Also, you can assume nu is no problem, yeah. The thing is the mu, right? The mu is the main thing. The mean is the main thing. Okay, very good. So let's see a Merton agent. So the agent actions are modeled by scalar value adaptive process A. A is the fraction of total wealth in stock. Okay, so the fraction, right? A. And then this well-known self-financing wealth process. W. The W is the wealth process, satisfy this so-called wealth equation, right? So that's well known. And the objective is to maximize by choosing the portfolio process, right? This terminal utility value. Okay, so here we assume we consider this utility function U, which is the power utility or serial utility. Okay, we just consider that. Okay, now for this problem, the classical model-based solution is given at least by Zalifopoulos, and actually it is very nice result. Okay, so you have like explicit solution and so on, so it can be solved completely. But then, of course, that model-based solution depends on the knowledge of those parameters, those coefficients, right? Which we don't know now, right? So we can't just apply that. All right, so as I explained in the beginning, we randomize, right? Because we want to do exploration. We don't know the environment, so we have to do randomization. So how do you model that randomization, right, mathematically? Well, agent choose time t action or portfolio by sampling from a probability distribution pi t. Okay, so now before for the bandit problem, it's because only you play machine one or not play machine one, so it's only two outcomes, right? So it's a coin. But now, of course, the actions are many possibilities, right? So you can think of it's like you have to design, instead of a coin, you have to design a dice, but it's not even dice. It's only 6 sides. It's many sides, right? And it's not even finite dice. It's an infinite dice because there are infinitely many possible actions, portfolios, right? So think about this pi is a infinite dice, okay? And then you throw it, you roll it, okay, depending on what it lands, and that is the action you are going to take, okay? So you choose action by sampling from, so you roll a dice, and then you take action accordingly. So here, this pi is a distribution value process, which we call exploratory control, exploratory portfolio. So now we are dealing with a density function value. The pi t itself is a density function of that randomization. Okay, it's a density function value the process. It's a bit complex mathematically, but we can define that properly. And under that pi, we have the so-called exploratory dynamic. It is given by this. this equation. Okay, so remember pi now is a distribution, right? So the equation is a bit different from what we saw at the beginning, the Wells equation. And there's also another Brownian motion. That Brownian motion, sorry, B bar, there's B bar. This B bar actually corresponds to the randomization we introduced. So there's addition, the third Brownian motion, right? Now this is called the exploratory dynamic. And there are lots of, there are other equivalent forms. This is not a unique form. There are other equivalent forms of the exploratory dynamic and their interpretations. There are a number of interpretations of this exploratory dynamic, for example, these papers, okay? But one interpretation you can think of that way, because you can repeatedly throw dice, right? You throw dice, so that gives you a control, a portfolio, and then you see the corresponding wells. And then you do it again. You throw the dice again. So there's another portfolio, there's another wells. So you do it infinitely many times. So this X WT pi is the average of those infinitely many wells process. Okay, so it's like an average on this dice, right? This pi. Okay, so this is one interpretation. There are others, as I said. For those who are interested, I don't have time to talk about those. For those who are interested, especially this, which paper? I think there's this paper. So there's a detailed interpretation, right? Okay, so here now we define. So with this exploratory dynamic, now we define our policies. Okay, so what do you mean by policy? Well, actually, here we only consider so-called Gaussian policies. Gaussian policies, okay? So measurable distribution value function pi lambda. So this is a function, okay, it's from time, right? So it reacts to time t, W is your wells, X is the factor, okay? So it's a feedback, so it's called the feedback control, right? So it maps from this to a density. So this PR is a set of density function. So pi is of this form. So this is a Gaussian, it's a normal distribution with a mean UTWX and with a fixed variance. Lambda divided gamma. Gamma appears in the utility function. Remember, gamma is the utility in the utility function. Sigma is the volatility. Okay, and equivalently, you can say this pi lambda is just a classical feedback control, feedback portfolio plus some noise. The N01 is the standard normal, right? With this variance term. So you add a bit noise to the classical deterministic control. Okay, it's the same thing, they're equivalent, right? And then the second condition is just, make sure that, under this pi lambda, the corresponding, the exploratory dynamics is well defined. So, okay, so that's not really important. Okay, the point is that now I concentrate on randomized policy, which is Gaussian. So I don't do other type of distributions. I only focus on Gaussian distribution, right? And this lambda is called the temperature parameter. So this, you can see this lambda certainly control the variance of your Gaussian distribution, right? The lambda is large, that means you have a large variance. That means, conceptually speaking, that means you have a larger, larger level of exploration. Okay, so you use lambda to control the level of exploration. So we denote the collection of all these admissible policy by pi lambda. So there's a lambda there, right? Okay, so this is Gaussian policy. So therefore, you can see we have an auxiliary problem. So for any given lambda fixed, the objective function is just, you look at this Gaussian policy and then the exploratory dynamic, right? And you can also define the optimal value function V lambda, all right? Okay, so this is the formulation. So we formulate an auxiliary problem. It's an auxiliary problem. In this auxiliary problem, dynamic is replaced by this exploratory dynamic. The control, the policy is replaced by this Gaussian policies. Okay, that's the auxiliary. Is that very clear? Right. Okay, so now the key result is we want to solve the original Merton problem without knowing these coefficients, by solving this auxiliary problem. Okay, so now I will show you how. So let's do some theoretical analysis. Okay, now first of all, because this problem is still, this auxiliary problem is still a stochastic control problem. So you can still apply HJB and so on, but this HJB is not for computation. It is for theoretical analysis. Okay, so you can write down the HJB equation. It's like this. And then we have this theorem, which basically gives you a solution to both exploratory Merton and classical Merton. Okay, so here is the result. So let's say phi is a classical solution of this PDE. Okay, and then this V lambda, remember this is the optimal value function of the auxiliary problem, yeah? The exploratory problem can be given by this. Okay, so this is the optimal value function of the auxiliary problem. Moreover, this one is the optimal policy to the auxiliary problem, this Gaussian distribution, where U star Tx can be written explicitly. Okay, and U star is the optimal policy for the original Merton's problem. Okay, now once again, this result is not to give you a solution to either the auxiliary problem or the original Merton problem, because we don't know those coefficients, right? So this does not give you a solution. However, this gives you, the importance of this theorem is to give you implication. Okay, so here let's study this problem. So first of all, theorem one characterizes optimal oracle solution. Oracle solution means that if you know all the coefficients, right, the model parameters. So this is a theoretical result not to be used to compute the solution to either auxiliary or classical problems. Okay, its importance lies in its implication. One can solve the original classical problem via solving the auxiliary randomized one. So if you can solve the auxiliary one, you get an optimal solution like this, then it's mean solve the original problem. So if there's a way to solve this auxiliary problem, then you're done. You solve the original problem. Okay, so that is the implication of this result. Okay, so this problem in turn justify our approach of employing a special class of Gaussian policy. Right? That is when you design these dies, you just use Gaussian. You don't use uniform. You don't use exponential distribution. Just Gaussian. And Gaussian is easy to sample, by the way, numerically speaking. Gaussian is easy to sample. So people like Gaussian. So I talked to some guys from Google. I asked them how they do lots of exploration, randomization. So they said, he told me, all along he used Gaussian exploration. So I asked why? Why Gaussian? Because it's convenient, because it works. But he didn't know why, what is the fundamental reason, right? So I told him that we have theory that supports that Gaussian exploration, and he was very happy. So you can kind of interpret that Gaussian exploration, right? So, right, and then moreover here, so you can limit admissible policy to only bivariate function W of Tx, because if you look at the result, so all you need to find is this phi, right? Phi is unknown, but phi is a function of only T and X. W is not part of the picture. See, so you know the theoretical result, and you know that later you only need to learn this phi function, which is a bivariate function, T and X. And also the mean, you see, it's a function of T and X, not W. Okay, so this also is beneficial in our later computation. All right. Okay, but then you may say, okay, so why? Okay, so the implication is if you can solve the auxiliary problem, which is randomized, then you solve the original problem. But you may say, oh, the auxiliary problem may be even more difficult than the original problem, right? Because it's randomized. Well, it's not, because once you have a randomized problem, then we have existing theory, which in those pentalogy, those 5 papers, you have algorithms that can solve them right away. Okay, so therefore, let me first talk about these slides. With Gaussian policies, we are in the realm of reinforcement learning, and thus we are able to apply or adapt the existing reinforcement learning methods to solve the auxiliary. So the auxiliary problem, in a way, can be solved right away because they are already theory. And later, I will also show that that algorithm does not apply when you don't randomize. So if you don't randomize, that algorithm doesn't apply. So you have to randomize. So there's a reason to randomize, technically even. Okay, so that's why. So this is the logic, right? Okay, so let's also talk a little bit about cost of randomization. Taking randomized policy is not free. It's not free. Utility value decrease because you introduce additional randomness and you are risk averse, right? So the utility value decrease due to additional randomness by a risk averse agent, okay? So therefore we introduce the so-called equivalent relative wealth loss called the ERWL. So that is defined to be a amount delta such that basically you are indifferent between you take a randomized policy and if we don't take a randomized policy, but with a smaller relative wealth. Okay, so therefore, in other words, this is the relative cost investor is willing to pay to engage stochastic policies. Okay, so you use this, it's like a utility indifference price, right? It's the same idea. So you use this to characterize the cost of exploration. Exploration is not free, right? Okay, so you play other machines that is costly. You need money to do that, right? It is also a kind of opportunity cost, right? It's not free, but we have a result which says that you can characterize this relative cost, which is in terms of the lambda. Remember this temperature parameter and time horizon. Okay, so we have some result in terms of the cost of exploration. Right. So now we can go through this. So this is just saying that we have this existing theory and algorithm for solving randomized policy. Okay, so in particular, we have so-called actor-critic approach developed for general stochastic control problem. So this AC algorithm learns value function, the objective function, and the policy function alternatingly and iteratively. Okay, so critic here really means the value function. Policy evaluation stage. Actor corresponds to policy improvement stage. Okay, so in other words, it suffices to learn to bivariate functions U star for actor and the phi for critic in that theorem. All right. So these are two formal theorems for policy evaluation and improvement. So the value function on an admissible policy and under a given policy, right, can be represented as this. So this is similar to the previous result, but previous result is about optimal value function. This is for value function of any admissible policy, okay? So it's also of this form. And then you define new policy. Given this policy, you define new policy, this U tilde, which is of this form, then you can show that, so the result says that this policy is better. So it's improved, okay? So in other words, basically, this theorem tells you you only need to learn this phi bar, this function, and this U tilde function. Okay, you are not able to use this explicit solution because you don't know these coefficients. So again, but it tells you that you only need to learn phi bar and U tilde so that you can improve. Okay, so this gives you such a theoretical ground. All right, so here we have the algorithms. Yeah, as I said, we only need to learn these phi bar and U tilde, and then you parameterize, right? You parameterize by a neural network. So cosine theta are finite dimensional parameters to be learned. So you use neural network to learn these. So this now become very standard. So the corresponding approximate value function, the improved policies are of this form, right? So then this is some sort of quick review of what's going on with this general algorithm for stochastic control problem, okay? So policy evaluation is equivalent to the martingale of certain stochastic processes, which in turn leads to data-driven martingale loss algorithm for offline learning and the moment condition for online offline learning, okay? So that's in our second paper on policy evaluation. And the policy gradient can be reduced to policy evaluation. That's actually, it's quite interesting. That is, policy gradient is a policy evaluation problem if you use randomized policy. If you don't use randomized policy, it is not. Okay, so that's our third paper. You know, and then there's this so-called little Q learning theory. Tomorrow, you know, in stats, I will talk a little bit about this little Q learning, in which value function and the little q function can be learned simultaneously based on also multimodality. So to learn this little q function is also policy evaluation. So all boils down to, all these steps actually leads to this conclusion. So if we only talk about algorithm, reinforcement learning is essentially policy evaluation. It all boils down to policy evaluation, okay? And policy evaluation, like I said, it, you know, basically, you know, it boils down to those Mardinger loss algorithm or moment condition, okay? So you basically can solve these this general stochastic control problem, randomized, I mean, exploratory. And there are also some implication for PD and the BSD. You know, maybe I just skip because, you know, if we can solve a stochastic control problem, basically you can solve PD, right? So you can use this method to solve PD, thereby get around this curse of dimensionality, right? So let me just skip that. Okay, so coming back to our specific Merton problem. So the moment conditions are like this, okay? I like this. Here, this G is the volatility process, which we assume is observable, is observable, right? But all the others are data, okay? You know, there's a test functions and so on. So let me just show you the moment condition becomes this. So these conditions only involves data. It does not involve the coefficients of. So like, you know, W. So A is okay. U is a parameterized policy, right? A is sampled from that Gaussian distribution with mean U hat. So you can sample. So this is also data, right? And this is the Wells process. You can observe. So everything is data. G is also data because it's observable. So this only involves data. So this is data driven. Okay, these conditions data driven. So with those moment conditions, we have the stochastic approximation algorithm, and you know, the problem can be solved in a data driven way. Now here I just want to mention this, just one very important point. Look at the second equation, the second moment condition here, this one. This one is for policy improvement. If we want to improve your policy to determine the new theta, you need to engage this, okay? You engage this equation, right? But this equation, think about it. If you don't randomize, then this AT, remember AT is sampled from the Gaussian distribution with this mean. But if we don't randomize, then A equal to U hat, right? They coincide, because if we don't randomize, then A is nothing else U hat. You have nothing to sample. So A hat is U, A pi hat theta is U hat theta. So therefore this is 0. So this equation gives you no information, 0 equal to 0. So in other words, if you don't involve randomized policy, you are not able to improve your policy. So this method works only for randomized policy. You have to randomize. So there's a technical reason here. Okay, you have to randomize. All right, so that's why we say, okay, let's work on an auxiliary problem which is randomized, then go back to the original problem. Okay, so that's why. All right, so maybe this is like a couple more minutes. Okay, so basically this is just that we use a specific Black-Scholes market, and everything is more explicit. For example, theoretically, this psi is like a linear function, and this Gaussian, this U is nothing else than theta is a sharp ratio, actually. It's a sharp ratio. So the more specific, and for that moment condition can also be more specific. And then we can do some analysis. And we have the, you know, we have the convergence. So this basically shows converge. This theta actually converge to the true theta star. Theta star we don't know, the oracle. So-called oracle value, we don't know, but it shows the convergence and convergence rate, okay? And this also shows you the error bound. The error bound is of this form. So this is like a, you know, a very standard, you know, machine learning error bound, right? So when n, you if you train sufficiently long time, then basically you're getting convergence and also almost like a zero error. Okay, and also there's a role of lambda, some discussion on the role of lambda, which I have to skip. But these are all in the paper. So let me just show you simulation results. Okay, so maybe I can show you. This is interesting. This is simulation. Okay, I just want to show you one thing. So remember, we assume this G volatility is observable, right? Volatility. So we studied two situations. We study a noisy observation. So actually, we can observe the volatility, but it is noisy. There is some Gaussian perturbation. Okay, it's noisy, and then we see what happens. So here, compare with the EST, this is the model-based approach. So if the observation of the volatility is exact, then actually the performance is not quite different compared to reinforcement learning and the model-based approach. So for example, the utility values are pretty close, right? And also the Wells loss are quite close. But in the noisy situation, that means the observation can be wrong. There's a huge difference, yeah? If you compare the utility value and if you compare the Wells loss, it's like huge. So in other words, the model-based approach fails when there's noise, okay? When your observation is not short. In other words, if there's error, equivalent saying if your estimation of the parameters has error, then you are really in trouble, okay? The model-based approach. And the RL is still very, very stable. It's very stable. Even with noise, its performance is very similar to the one without noise, okay? So I hope that make a point, right? And then we also did some empirical study. And here, I just want to show you something. So this is the out of sample performance of different methods from 2000 to 2025, February 25. So this is buy and hold, okay? And this is model-based approach. So if you compare the Sharpe ratio, the two RL methods certainly beat most of the matrix. But I want to draw your attention to the recover time. The recover time, the recover time is like, the market crash, right, to the bottom, then recover to the previous high. So how long it takes, to recover to the previous high, basically that time. The reinforcement learning method takes only 282 days or 200. Compare with buy and hold and the model. The model is really messed up. 4,200. This is really bad. And also maximum drawdown. Maximum drawdown is much smaller, right? Compared with buy and hold. The buy and hold basically the index in the S&P 500, right? And this is model-based approach. Okay, so you can see that reinforcement learning strategy indeed is very, very stable, right? Okay, so let me just conclude. So the central component of RL is exploration carried out by policy randomization, right? Randomization. So yeah, one of the questions is stock data exogenous and hence there's no need to explore. But we argue otherwise in this case, in this paper. RL, including policy randomization, can go beyond the conceptual role of exploration. It can actually be used also as a technical role. As I showed in this moment condition, if you don't do randomization, then you don't have policy improvement. So you're not able to improve, all right? So a key insight, exploitation trade-off in the Merton setting is not only about information gains versus payoff losses, but also about the strength of the learning signals versus their reliability. And data can be endogenous. Now, I think that's another insight. That is data, not like in the classical model-based scenario, data that are mostly exogenous. Data can be endogenous. Randomization adds data. Okay, so actually data is part of the solution. So data is endogenous. And randomization adds data for training, but not for estimating a model better when data are insufficient, okay? And here also we use the so-called off-policy learning that is trained with randomized policy, but when you actually execution, you don't roll a dice again. You just use the mean. Remember, the mean is the optimal solution, so you just use the mean. You don't throw dice. You throw dice only when you're training policies, okay? So I think these are some of the insights that we draw from this work. Thank you very much.
Okay, thank you very much.